Hello friends, I'm George, and I'm here to describe my experience building a silent computer for video production. So let's get to it, beginning with why I started this project 4 years ago and what I learned along the way. Hi, I'm George, and I'm nearing the completion of a project to build a battery-powered, fanless, energy-saving and high-performance computer. It was built pretty much from the ground up, part by part, with the motherboard, starting with the motherboard, which was an ASUS motherboard. The question I would like to answer right off the bat, I would like to address why one would build a battery-powered, fanless, energy-saving, high-performance computer. Okay. 1. Noise. It's fanless. This is I'm trying to build a computer that's completely fanless, simply to eliminate noise. There are times when you need a fan, but most of the time you don't. 2. This is a battery-powered computer, and the purpose of that is to eliminate AC hum so that I can do video editing. This is a battery-powered computer to allow greater mobility, allowing remote filming of sound events like karaoke events out in the woods. It's fanless to avoid the need to replace moving parts. And you all know how when your computer starts out it sounds pretty quiet, but after a year all those little fans begin to rattle and roll and you need to replace every one. And there's a lot of fans in computers these days, especially the high-powered ones. This computer is low wattage, partly to meet the requirements needed to make a battery-powered fanless PC, but also to reduce heat generation, particularly in ambient outdoor environments or indoors when you're in an unconditioned apartment and it's 95 degrees. This computer also wants to be a high-performance computer capable of sound and video editing on large storage drives, and we're basically aiming for solid-state terabyte or 2 terabyte drives to be the medium for storing video and audio clips. There are trade-offs. The trade-offs are performance versus speed. You can have the fastest computer, but it's going to be high wattage. It's going to need a lot of fans. So we traded off some of the speed in order to have lower wattage, cooler running, and run it without fans. Another trade-off is cooling efficiency versus size and mobility. Also, another trade-off is the cost of a do-it-yourself build versus just buying a Dell laptop. I wanted to push the envelope as far as possible to get a computer that was capable of running outdoors on a truck battery, being wheeled into the woods on a hand cart with a couple of marine batteries for karaoke drum circles out in the woods where we get really crazy. So without any further ado, here's that computer. Okay, at this point the two sides and the back were put on the hexagonal studs, 9 of them, whoops, need one there, are in, ready for holding the motherboard in place against the back side. This is an ATX motherboard. When the two sides are on, The back plate can be put on with 4 case knurled nuts and 2 screws under the bottom, and then the motherboard fit into place. And you can't see, but this hole fits, this hole fits, and that hole fits. The other 6 other holes don't have proper holes drilled and have to be drilled. So when it's fit into place with just a couple screws, holes will be drilled, and then the motherboard can be screwed in properly on top of the risers. The next step of this computer build is to prepare the motherboard for accepting an AMD Ryzen 5 3600 CPU, which is going to go here. There's a modification to the HD5 case, cooling case, that wants to take out these stock brackets that hold the fan and replace them. Instead of having a motherboard backplate, to replace them with little feet that go under each hole and come through like that, and then they're screwed into there. Okay, so for the next step, I'm going to go ahead and put these 4 CPU cooler holders on the bottom of the board in the proper hole, and they'll be they're stuck on. They'll be stuck on with a little bit of tape that holds them to the bottom so that you can screw in the heater. So the reason these backplate screws were replaced with the ones from the HD Plex H5 case was because they're a different size thread that holds the CPU heatsink cooler from the ones that came with the motherboard. So the other advantage to having these mounted is that now I can go ahead and install the motherboard and use that as a base in which to install the heatsink, rather than setting it on furniture and trying to juggle electrostatic ground strap, which you have to do anyway, but it'll be a little more convenient this way. Okay, preparing the heat sink assembly. These little clips go in with the big hole side up into the end of the racks. Oops, like that. And then the screws go into the and then that's ready to go onto the chip after we put the Arctic silver on. So for the AMD setup, as opposed to the Intel, there's supposed to be a little play in the racks, and they have to be adjusted back and forth a little bit until they're just on top of where they're going to go into the screw holes that are mounted on the back side. I'm going to apply the thermal paste in the center as a pea-sized dot. Okay, the 4 screws are in. They're snug. There is a tiny bit of play that I believe is intentional. It's only sideways, it's not down. There's good solid downward pressure even on all 4 of those. I'm going to put it into the rack now, but I want to show you what I used to mount this on. It's a handmade anti-static board. And what it is just a few sheets of a few of these baggies that are electric static metal covered bags, and inside of them is a aluminum sheet. Okay, and that aluminum sheet is sitting on top of a foam pad to give it softness, and the aluminum sheet is also held down by just some metal paper clips, and it's grounded to a power supply that's plugged in that's off, so it's grounded to the ground, earth ground, and so is my wrist strap is also grounded. So, and the purpose of that is to dissipate current, and the purpose of the strap is to eliminate current. The final touches of thermal paste are going onto the CPU now. A very minimal amount of paste is applied. There are 8 heat pipes that go in this. Each has a different shape, and they go in a specific order, starting with the 2 in the middle in the diagram. They're going to have to bend a little bit before they get finally in, but that's how they go. And so on. At this point, the heat pipes have been held to the case side with 3 plates, one of which was very close to the bend, so I shaved it off a little bit so I could get it there, but it could have, there's another set of holes that it could have been mounted here and here. There's 3 plates, 4 were sent. The next step is, so the plates are loose, the next step is to mount the aluminum heatsink on top. That's already been covered thinly with thermal paste, and it will go right here and then be wiggled into place and screwed down, and then everything will be snugged up. Alright, well, so the CPU heat pipes are in. I did have to cut away one of the little tabs on each side of this side, 2 tabs actually, to make room for them. The top just need to be shaved off with the razor. It was not a big deal. They went in pretty good. They were well made, well machined, and it's nice and solid now. The M2 drive, solid state drive was put in, some DDR4 memory was put in, and a power supply and an on-off button was installed. And what I'm going to do is go ahead and bench test it. To bench test it, we're going to go ahead and put the graphics card in with the graphics card fan installed so that we can test it and make sure the whole setup works before removing the fan on the graphics card and installing the graphics heat pipe setup, which will go on this sidewall. So what's on the board right now is an M.2 solid state drive, the graphics card running under fan cooling, the completely set up heat pipe cooled CPU, 2 DDR4 RAM chips, and I've got a power supply that doesn't fit in the board, so it's off to the side. And I left the fan, that's the CPU fan, on because on the bench, to bench test it, I wanted to be sure that the computer was sensing the fan speed, and I wanted to measure the temperature cooling ability of the heat pipes before I went on to do the same thing for the graphics card. This is a Gigabyte low profile video card which did not fit very well. When the fan was taken off, you can see these 4 holes were mounted over the fan, and a big glob of thermal paste was put right there to conduct it across about a 1.5 millimeter gap. To make this card fit onto this copper heat plate without bumping into these components here or even along here, an area that just covered where the 4 mounting holes are was milled around on the copper heatsink plate. There's a couple scratches, but the 4 holes here match these 4 holes, and it's going to get mounted on like that through those 4 holes. There's not a lot of clearance. The milling was done so that the raised portion that's going to contact the chip doesn't touch any of the components here, and just in case, I'm going to add a little piece of thermal tape here and probably here, just to make sure it doesn't wobble into these metal components. When we milled this, we went ahead and let the holes go clear through, so it'll be important not to let those holes be filled beyond the bottom where the heatsink pipes have to go. But the springs will prevent that, so it doesn't have to be torqued all the way down. One point to note is that this milled area is very tightly made to just barely overlap the edge of where the screws are, so that there's not going to be any metal within 2 millimeters. That's the thickness of this raised part here. Here you can see the heatsink after it's been screwed on with these 4 screws to the chip, and it looks like it's right just touching the top of the chip from the side, and the spring-loaded screws still have a little give, and they don't protrude through the holes that came through. So the only step is to repeat this, take this off and put it back on with a dab of Arctic Silver. Alright, after I got to the point of putting this together and starting to put the heatsink on, I realized that the graphics card was blocking these buttons. They're not really used, they're just for testing mostly. They're a start button, a restart button, a safe mode button. So they're not really going to be used except for testing. But it just seemed a waste of some really good functionality of the board to completely block it when the original setup for the board was mounted so that the board would be over here. So I made a special mounting bracket and moved the graphics card over by about 1.5 centimeters, so that when you install it about right there, you can barely access, but you can access these buttons over here. So that was modification 1. I should say that I'm having second thoughts about why I bought this board in the first place. The reason I bought this board in the first place was because it's an ASUS Crosshair 6 Hero with Wi-Fi. I bought it because it was the only board that was backwards compatible with the old style mounting bracket, in case I wanted to use some old school type early cooling units on the CPU, and once I decided on this design, I didn't even need it. So I made this modification with the card moved over a little bit. But mind you, look at, once you install the card here and you expose the buttons here, you still lose functionality for 3 full expansion sockets. The other modification I made was to make sure the surface of this heatsink was totally flat and smooth, so I polished it up with 4000 grit. I also made sure there were no burrs on the holes. The back plate is mounted, and the copper heatsink is screwed into the new slot. We're going to go ahead and put the graphics card into the modified card holding slot. Okay, at this point the cooler is installed for the graphics card here and the CPU here. The graphics card is mounted sideways rather than vertically using this flexible strip that comes as an add-on from the HD Plex company, and it plugs into the PCIe plug that normally would hold the card vertically. So the disadvantage is that you lose a couple of slots under there that are no longer accessible. And that's a pretty bad disadvantage, I will have to say, for the trade-off of having to put these heat pipes on the side. So I look to a future design build with a more of a tower design where there's more room in the cabinet to put things, and it doesn't have to all be on top of the motherboard. But that's the way this one goes. So we're going to give it a try right now. Okay, thanks. Bye. Okay, I'm starting up the computer. The build is just about complete. The last 2 pieces were to replace the Silverstone power supply that I had in here with one that actually fits inside the case. I thought I could save some money by using the Silverstone, but it stuck out and I didn't feel like modding the case. So it's starting up. The ASUS board starts up, and when it says 40, that means it's ready to go. As you can see, Windows is up and running. In another video, I'll continue to mod this out with battery-powered setup where we take out the AC power completely and make it a portable, basically heavy-duty laptop that goes into the woods for filming and performing in remote environments without AC power. This is a point where we put in the power supply, and putting this power supply that I got, which is a 400 watt 2-piece unit. One is the AC converter, the other is the distributor for the DC feeds. This power supply is by HD Plex, and unfortunately it doesn't match the HD Plex case size. You can't put them side by side as illustrated by the guidelines etched on the case. They actually just don't fit side by side. No way will they ever fit, nor is there room on the side of the case or anywhere. So they have to be stacked some way or another. And so that meant I had to use these plates that came with the risers, so they would be mounted on a riser. And so I finally, after a lot of trial and error, I figured out that the DC distributor part, called the DC-ATX component, would go on the bottom and still leave room for the AC converter part to go on top. There's only enough clearance for about an extra ½ inch when these two are stacked, and I wanted air between them to help with cooling so that the optional fan would not kick in. It kicks in above 200 watts, and I don't want a fan to have to kick in the unit. I want it to be cool. I'm still thinking of walling this portion off and making it an external power supply to help keep the board cooler. And I'm also planning to make this whole AC converter part optional so that it'll just run off batteries, and that's all that you'll see if that's the case. Probably I want it to be both ways so that it can run either on batteries or AC, in which case this will still be here, approximately that position, and there will be a switch to switch back and forth between DC or AC. Okay, so I'll go ahead and screw that in, and then we'll talk about the final parts of putting the case cover on. So I ran a few benchmarks, not many. I don't really do benchmarking very often. But anyway, I used Cinebench 20 and Cinebench 15, and on Cinebench 15 OpenGL it ran 164 frames per second. And again, I did it a second time and it ran at 178 frames per second. I also ran it at Furmark for 1 hour at 45 frames per second to burn it in, basically. And it got hot. It got up to 66 degrees centigrade, and that's when it leveled off. I didn't want to run it too hard, but anyway, so it's burned in pretty good. Okay, these are the lessons that I learned from building my own silent PC. First lesson, ask yourself why you want a silent computer. Why would you build it for yourself? Is it for recording audio where absolute quiet is necessary? This was my main reason. Or perhaps you want to be off-grid. Or is it because fan noise is driving you nuts? Well, there are whisper quiet PCs available, and they have super quiet fans. Is it because you want to learn something new and different? If not, then the Silent PC company builds and markets fanless PCs at a reasonable cost. But let's suppose you're just like me and you want to build your own. Okay. Then in that case, next lesson. Be prepared to modify hardware. Even if you're building from a proven design, expect that some of the hardware will not fit together right. The case, the motherboard, the CPU, the power supply, the solid-state drives, the graphics card, and the conductive heat pipes all need to be designed together as a unit. The motherboard is probably the most crucial piece of hardware to base your design on because it isn't easy to modify the circuit board. For instance, even though my build is similar to a fanless computer made by Silent PC, their design only needs one set of heat pipes for the CPU, since the graphics display circuits are integrated into the AMD CPU. I wanted a dedicated Gigabyte 4K graphics card for better video processing. But the drawback was this required cutting a new set of mounting holes in the case housing and having to custom mill a copper cooling plate at a machine shop that would fit the case to the graphics card cooling pipes. Okay, third main lesson. Overclock speeds versus silence. It's fact that the computer industry is geared toward ever greater speed, not silence. When I started this build, I chose an AMD 3600X 6-core chip, mostly for budget considerations. I chose an ASUS Wi-Fi board because it had backward compatibility with the CPU mounting bracket. Despite having to modify the design considerably, my computer is still humming along fine after 4 years, smoothly recording music and videos like this one. My biggest disappointment was that the AMD CPU is not designed to be fanless. Overclocking the AMD chip depends on automated fan speed settings for half a dozen fans, and this makes it nearly impossible to maintain the fans in an off condition. The slightest amount of overheating either turns on fans by some unknown algorithm, or shuts the CPU down, or allows the chip to get really hot really fast. In addition, there is no information from AMD on how the allocation of processing power between the cores affects CPU temperature. So in the end, I opted to set the CPU to stock speed without overclocking. Well, actually, I have the CPU slightly underclocked, and that keeps it at a rock steady 55 to 60 degrees centigrade, or less than 140 degrees Fahrenheit, even when working it really hard. Plus, I sometimes use that fan for backup cooling in August when the temperatures are 100 degrees and there's no air conditioner. So, in summary, if I had to do this again, I would try the same build with a different case, a different motherboard, and especially I would switch to an Intel chip, which I believe might have more flexibility for manual overclocking. Okay, that's it. Bye. Thanks. The computer works great. I think this computer is going to be a lot faster than what I've been using, which would take all night long to render a 1-hour movie in HD. I'm hoping that this will be rendering the same movie in about a half an hour or less. Okay, thank you.